In this lecture, we learn how to analyze performance of a computer system, and we talk about relative performance between two systems. Before we can talk about the performance of computing systems, we need to start understanding performance a little better. In a computer system, the performance to do any given computational task will depend on a number of things. For example, which is the algorithm that you have chosen to do the task? The algorithm will determine the number of operations that are executed to do the task. The programming language, the compiler, and the architecture that you choose also will influence your performance. Will determine, for example, the number of machine instructions that are executed to do each one of the operations in your algorithm. May also determine the order in which you access memory and some other factors. So the processor and the memory system will together determine how fast the instructions can be executed. And the input-output system, including the operating system, will determine how fast input and output operations are executed. So combined, these different factors influence performance. Therefore, when you talk about how much time it took to do a given task in a machine, we're going to have to talk about all the different aspects of performance. And in this and the next lectures, we'll focus on decomposing that time into its components so that you can better analyze the performance of a computing system. First, let's try to define performance. And we'll start with this comparison of airplanes. If I ask you, which airplane has the best performance? Is it the Boeing 777? Is it the Boeing 747? Is it the Concorde, which is not flying anymore but used to be the supersonic airplane? Or is it the Douglas DC-850 airplane? You may jump and say, well, the Concorde is the best performance because it's the fastest airplane. And you'd be right if my problem was to find the fastest airplane to get somewhere. However, if I compare the airplanes with different metrics, I'm going to have different answers. For example, if I want the cruising speed that is the fastest airplane, my problem is to go from point A to point B in the shortest amount of time. My choice would definitely be the supersonic Concorde. However, if my problem is to transport the maximum number of passengers in any given trip, then I'll be choosing the Boeing 747 over the other airplanes because it has a higher passenger capacity. If my problem is to get the furthest without having to refuel, then my choice would be the Douglas DC-850 because I could get much farther in that airplane without having to stop to refuel. And if my problem is the problem of transporting the maximum number of passengers, perhaps in many different flights, in a certain amount of time, then my choice would be the Boeing 747 because it has a higher passenger per mile per hour. Therefore, when I ask about the best performance, one of the questions is which is the task that you want to do, that you want the performance for. Let's consider two measurements of performance that we can do in computer systems. One is the response time, and the other is throughput. The response time is how long does it take to do a single task in the computer. And the throughput is the total work done per unit of time. For example, if you want to book a flight in a given website, what you care about is how long does it take for you to do your booking. But from the company that has the website, it might be more important to know how many bookings can be done per unit of time. For example, how many bookings per hour can the processor handle. So to illustrate this, let's look at a picture. In this case, I have 6 different tasks that I need to do. They are represented by different colors here, and I have the time that it takes to do each one of the tasks that I have. And in this case, you can assume that there is a different user, a different person waiting for the end of each one of those tasks. So in this case, I'm interested in how fast I can perform each one of the tasks. However, if all the tasks are being done by the same person and that person cannot leave the room until all tasks are done, it doesn't really matter the individual runtime for each one of the tasks. What matters is the total amount of time that you need to do the tasks, or the number of tasks that you can do per second. So that's the difference between latency measurements and throughput measurements. For example, if I have the RISC-V FE310, which runs at 320 megahertz, and I replace that by the RISC-V FU540, which runs at 1.5 gigahertz, so a processor that has a much faster clock speed. So this is a much faster processor. What will happen with the response time? The response time will be lower, which means that I can finish a task in a shorter amount of time. But the throughput will be higher because I can do more tasks per unit of time. Now let's consider another situation where I do not get a faster processor. I have a given processor and I replace it by a system that has multiple processors of the same kind. So in this case, the response time will be the same, and in some systems it can be even higher, which means that it can get slower because you have to coordinate between all those processors. But the throughput will be higher because I can assign a different task for each one of the processors, and I can finish an ensemble of tasks faster. So let's talk about relative performance. And to talk about relative performance, let's analyze a little story. Let's suppose that I need to do a trip from Edmonton to Calgary. And let's assume that the distance is 300 kilometers. And here I have John, and John has a cute yellow car. And in this car, John can go at 100 kilometers per hour. The time it takes John 180 minutes to go from Edmonton to Calgary. Now here I have Mary. Mary likes fast cars, and she has a heavy foot too, so she will go at 200 kilometers per hour between Edmonton and Calgary, and she's gonna take 90 minutes. The questions that we want to ask now is, what's the performance of each one of John and Mary when doing the trip from Edmonton to Calgary? And performance in this case will be measured by the distance that they go divided by the time that it takes, we call it execution time, the time that it takes for them to do the task. So in the case of John with his yellow car, he goes the 300 kilometers in 180 minutes, and Mary does the 300 kilometers in 90 minutes. Therefore, if we are analyzing their performance, we can say that John does one trip to Calgary in 180 minutes, and Mary does one trip to Calgary in 90 minutes. If we ask now which car is faster and by how much, how would we answer that question? What we need to do is to take the performance of John and the performance of Mary and divide that one by the other. And we will always divide the higher performance by the lower performance because we want to know how much faster Mary is compared to John. Well, the performance of Mary is one trip to Calgary divided by 90 minutes, and the performance of John is one trip to Calgary divided by 180 minutes. Therefore, the expression, the trip to Calgary will cancel in the expressions, and I have 180 minutes divided by 90 minutes, which is 2. And we'll say that the red car is 2 times faster than the yellow car. Notice that if I had reversed this equation and had the performance of the yellow car on top of the red car, I'd get 0.5. And but we don't talk about performance in English in common language. We usually doesn't say that something is faster than the other by a number that's smaller than one. That's why we'll choose to have the higher performance on top of the equation when comparing. But now let's translate this to something that's more related to computers. Let's say that my task now is to render an explosion in a movie. And I have the Skylake Iris Pro P58 to do this rendering, and I have the NVIDIA GeForce GTX. Let's say that the Skylake takes 180 minutes and the GTX takes 90 minutes. The question now is, what's the performance of each one of those processors? And the performance of the Iris one will be one explosion in 180 minutes, and the performance of the GTX is one explosion in 90 minutes. Now, if I want to compare, then I have the higher performance divided by the lower performance. So I have that the difference in performance between them is also 2, like in the previous example. And I will say that the GeForce GTX is 2 times faster than the Iris Pro P580 for the rendering of this one explosion in the movie. So we did this parallel between a trip between Edmonton and Calgary and the rendering of an explosion in a movie to illustrate that what we already know about performance still holds when you're talking about the performance of computers. The relative performance is 1 divided by the execution time. So if I compare the performance of X with the performance of Y and I obtain a number N, this is the equivalent of dividing the execution time of Y by the execution time of X. So notice how there is a reverse of the order in the division. We start with the higher performance on top and the lower performance on the bottom, and that's equivalent to having the higher time on top and the lower time on the bottom. And we always say that X is n times faster than Y, and we're gonna order them in such a way that this n is greater than 1. Another word about measuring time: when using a Mac or a Linux operating system, you have the time function. When you run a program, you can put the word time in front of the program, and if you are taking 201, you can do that with your 201 programs and you can measure their time. And when you measure their time, you get numbers such as the ones shown on the slide. You have the real time, the user time, and the system time. The real time is the elapsed time that accounts for the processing plus the I/O plus the system in general plus the idle time. The user time is the CPU time, is the amount of time that the CPU is busy. And the system time is the time spent in the system. In this example, you see that the elapsed time, that's the real time, is shorter than the user time, because this was measured in a machine that has more than one processor, so the user time was actually divided between different processors. There are multiple cores in this machine. So a recap of the second part of this lecture: we have learned the difference between latency and throughput. Latency is when we have different people waiting for each one of the individual tasks. Throughput is when you have a single person waiting for all the tasks. Another way to say that: in a web service, for example, latency is the amount of time that each one of the customers have to wait for their transaction to happen. Throughput will be the number of transactions per minute or per hour that happen, which will be a concern of the company that's providing the service. We have learned that performance is the inverse of the execution time, and that if I divide the performance of X by the performance of Y, this is equivalent of dividing the execution time of Y by the execution time of X.